Hi, I'm Jesse Burns. Thanks for coming to my talk. I'm from ISEC Partners in San Francisco, and I've been looking a lot at Android for the last year. It's a really cool platform, and I'm going to talk a bit about how we can explore Android, what sort of information sources there are on there, and I've been looking at a lot of different Android distributions and helping some carriers create Android systems that are safe, and or manufacturers create devices that are safe. And I want to talk to you a little bit about some of the issues that you kind of run into and what you might want to look at if you've got a new device and you're trying to understand what's the attack surface, what are the new features, what's cool. So I'm going to start off with an overview of the security model. This is targeted pretty heavily for developers or very technical users. Hopefully, and of course security experts, researchers wanting to look at the platform and figure out how to apply their Unix skills to this platform. I'll talk a bit about what's new there, and then I'll go into exploring droids and take a look at an example one, introduce 4 tools that I'm releasing that help us figure out what's going on a distribution. And then conclude by talking a little bit about hidden packages, root access, proprietary pieces of the platform, and some of those common problems I've run into that you need to look out for. All right, so Android security leverages Linux kernel security, but adds Android permissions and other security concepts from mobile platforms. Applications are isolated, meaning that a program for editing notes can't read your email. This means that applications need to be identified individually from each other, and each is assigned a user ID and a group ID when it's installed, just like creating a Unix user. Some important UIDs and GIDs are, of course, reserved for system use, just like it would be on your Linux machine. And here you can see the process list of an Android device. Notice that many of the processes run with different user IDs, although obviously the system has only one user, the interactive user. Some of the applications have their own identities, and some share an identity. So we can see COM, this package sitting here, the COM Android IM and the Android process IM are both sharing a user ID, that is app0, and these are closely related programs that are from a single vendor. The abduction game, which is the little cow being beamed up into the UFO, that is running highlighted in red as app45. So it's got a user ID of 10,045, and it's going to be the only thing on the system running with that UID. So when you install it on your machine, by the way, you're going to get a different UID. The ID is specific to the system that it gets installed on. It might be 45 if you happen to install your apps in about the same order I installed mine. So Android security model. Android uses both Android permissions and users and groups to represent the actual rights that users have. So in the top view, we can see this familiar ADB shell. The ADB shell is the debug shell that you most commonly use to talk to an Android device, which has been configured for debugging. So if you find an Android device on the bus, this isn't turned on, you have to take your device and say, I want debugging turned on, and then you can hook up your debugger, get a nice shell on it. And I've typed ID into all of these shells, and you can see all the different users and groups they're running as. So that top one, being the debug shell, has a bunch of groups that the other ones don't have, like graphics, input, log, ADB, and inet. And these can be used to secure files on the system, and they can be used by the Linux kernel to enforce security protections for this application. They can also be used to stop people who don't have those rights, of course, from accessing those same features. So there are also Android permissions like dump that aren't expressed with Unix groups and aren't visible from the ID shell command. So my ADB shell runs as the shell user with users and groups under 10,000, and that means it's also a special built-in, right? The shell isn't one of the normal user apps. The middle app, on the other hand, is the sample terminal app, and it is a normal user app. It installed, in my case, with a UID of 10,026, and that's typical of the range for installed applications and processes. It also has the inet permission. That's because I've specified in the user's permission tag that this thing has to access the internet, and the kernel is what's enforcing the internet permission, and the kernel doesn't know about Android permissions. It only knows about Linux groups and Linux things. So the Android runtime systems granted me the inet group membership so that the kernel can decide whether or not I'm allowed to create inet sockets. And then finally, pterminal. It's a really trivial terminal app that you can download. It lets you type ID just like all the others, and you can see that it only runs as itself. It doesn't ask for any permissions, doesn't have any users or any special groups it's a member of. So the types of applications that are made for running on Android are made up of activities, services, broadcast receivers, content providers, and instrumentations. You can also have a program like ls or strace, but that isn't how Android software usually works. Android software, a single package is called, or a single Android application is called a package. The package is kind of the name for a collection of these activities, services, receivers that make up everything in that. You could have any combination of these. You could have a service and a receiver and an activity, or 10 of them, or just one of one kind. So I have a list here of these. I'll just go through it real quick. Activities, these are screens that actually do something. So if you write a Hello World application, you built an activity. It pops up. Your dialer is one of these. Services, these are mainly to make iPhone users feel real jealous about the fact that their stuff can't run in the background. This is for, downloading files in the background, playing music, stuff like that. Services are different from system services. These are ones that end users actually write themselves. Broadcast receivers, these are asynchronous events that come in. So I I can say, hey, whenever the system boots, I want you to call me. And the system will actually fire up your app and call you and say, hey, the system's booted, right? Or it can warn you when you're running low on space, or when a time event happens, or send you a broadcast when an SMS comes in. Really handy for writing things like clients that have to react to something that's going on, and that you don't want to have sitting there running, wasting memory all the time in a very resource-constrained environment. Instrumentations are really rare. They're content providers are these shared information stores that can be secured nicely with Android permissions, so like that dump permission. They don't have like file and group IDs. They're not secured with Unix file permissions, so they can be a little bit more flexible. They also are good for storing relational data, because you can do things like put where clauses in, stuff like that, and share them between totally unrelated applications. And instrumentations are some debug functionality used for testing. Actually says somewhere in the docs that they don't show up in runtime systems, but they do. And all of these are secured with permissions like these. So read contacts, simple permission lets you read someone's contacts. Brick, not so simple permission, lets you make the device into a brick. So see manifest permissions and an Android manifest near you to find out what permissions are supported on your phone and which applications might turn your phone into a brick. So Android also, to all these new toys, have to communicate with each other. The Android runtime takes care of a lot of this communication. It handles, when you say, I want to view a web page or something, it'll create an intent, and the intent has in it the URL that you want to visit, and the system dispatches that to the browser, and the browser fires up and does your browsing loads up the URL for you. So they're kind of like a hash table. You can put lots of data in them, but they also have a little bit of routing data in them. They have an action that you're trying to accomplish, perhaps, or it could be just a notification action. And they can have types, so you can say, this viewer only knows how to view GIFs, not JPEGs, and they can have schemes and hosts and all kinds of crazy stuff. So they can be implicitly or explicitly routed, and this one I've printed out here is the string representation of the intent you'd use to start that abduction game, if you want to help save cows. It has an action of main and a category of launcher, which means that this is it being launched by clicking it in the home menu. And it has a specific component set, meaning that the person who started this knew exactly what they wanted. They didn't want the runtime to help them figure it out. So having isolated applications with unique permissions creates security challenges that are not unlike those commonly found on multi-user systems. Funny, kind of, as most mobile devices are really the ultimate single-user platform, right? You've got this device, and it only has one interactive user, and that person owns it. And but here we are having to build multi-user security in. So sharing a UI and a device between multiple users is actually really tricky. It's not something that a lot of operating systems tackle. And the need to secure all that input is obvious, because if you don't want people reading your keyboard entries, because you want to stop them from reading your contacts, you better lock that down. So it's somewhat like what Vista tries to do with user interface privilege isolation, UIPI, which is that system for stopping applications from seeing each other's keystrokes or events. Fortunately, it's done without all the pop-ups. And anytime you are trying to build this kind of security mechanism where you have different apps running with different rights, you have the possibility that there could be some kind of malware threat or somewhat kind of phishing attack-like threat where you make a block stacking game that maybe it looks like your contact application, and so you accidentally type some contact information in there. It's sort of a somewhat lamer attack, and it's definitely not impossible, but it gives you a much kind of different playing field. Anyway, one weird mistake you see a lot of people make when they're looking at Android is not understanding the difference between the Java language, Java, and Java applets. Android is programmed in Java, the Java language, but the code doesn't run in a Java virtual machine. It's not a Java sandbox. You can have arbitrary code execution in Java. If you can write a program, for example, I showed you 3 terminal programs, 2 of those are written in Java, right? Obviously, the thing can run shells, right? It has arbitrary code execution. It's not a Java sandbox. Where the sandbox is it's a Linux sandbox, right? Which is a much better place probably to be playing. You've got this operating system that's maybe a little more mature. It's certainly older than Java. And we haven't seen a huge amount of Java security at the security manager level recently. It was really popular in the late 90s, but it's kind of died away. So Android has highly privileged system services running on it, and these are not services of the kind that I was just talking about. Those services are services that users install. They subclass service. These are system services, so you can think of this like your window manager, right? These are services that are always running. They don't get swapped out. They don't get activated or deactivated. When the system boots, they fire up. When the system goes down, they go down. And an example of this would be Audio and Surface Flinger, and those are native code, so they're written in C++ or C. And others, like Activity Manager, are written in Java. They have the same rights, the native and the system ones. They're all running as the system account, and that's a very privileged account. It can do essentially what it likes. And when I say the Android runtime system, I'm actually talking about these services, these system services. So when I send an intent and the system takes care of routing that, that's Activity Manager, the system service, taking that intent and finding who's going to be started and sending it off. So on my Cupcake 15R3 emulator, I only have 42 services running, and this is a list from Annalee's phone. She's got 45 or so, 44, and that's because the emulator doesn't have Bluetooth. So it kind of makes sense. You can call context.getService, and that'll expose you the service manager's service list. And it's not actually the real services. You can get those, and I'll talk about that a little bit later, but the services that you get from getService are actually nice, friendly wrappers that show you just the public parts, right? So you get back the pieces that you should use as a developer, not necessarily the full attack surface that you might want to use if you were doing security testing or trying to figure out what was going on with malware, right? All right, so let me sketch out the simplest system service that you can find on an Android device so that you can get an idea what these things look like. This one is the clipboard service. iClipboard.adl is the Android interface definition language file that defines it, and it's got only 3 methods, the most sophisticated of which is right here, 2 lines of code, and it just takes information, stores it in the clipboard, or takes information and gives it to you, or checks whether or not there's anything there in the clipboard. At no time does any security check get performed. So every process can call this method. It's a system service that's exposed as a binder interface to absolutely everyone. Anyone can grab this binder and make these method calls, and no security checks happen before they're executed. So there is some synchronization to make sure data doesn't get corrupted, but there isn't some check to make sure you're authorized. So if you think about that, a clipboard permission doesn't really make much sense. Everything reasonably uses the clipboard, and you just have to take your chances. It's an untrusted data source. And it's by opening up a file like this and taking a look at this thing, the clipboard service.java, that you'd figure out that this data source is totally untrusted. Here's a nasty system service. This is a very small part of an invocation of Surface Flinger. Surface Flinger is the system service that handles drawing stuff to the screen. And it's a system service on the other side of the simple complex divide. It doesn't even have a nice ADL interface or even friendly proxies for calling it, like a Java object from Java. It isn't even part of the public SDK. But like all system services, it's part of the platform's attack surface. Here's an example of the kind of hackery that's used to call it. This is actually not too bad, as no parameters are being passed and no data is actually being returned. Still, the function is assumed to be the first call transaction, which is just in a binder interface, the first method defined in it after ping and dump, which are the default built-in ones. And it's not pretty. So Android has two new kernel mode interprocess communication mechanisms. Binder. So binder is these transactions that are atomic and aren't typically named, except for the bootstrap one, which you use to get to all the other ones. And making a call on a binder interface is called transacting. Binders use the parcelable protocol to move structured data around. So this includes parcelable objects that you might write in Java, primitives, binders, lists, and file descriptors. The protocol is really critical for the security. So you've got this native kernel interface. It can do all this great stuff. But if you don't use the ADL compiler and the protocol that defines, you won't get a lot of the benefits. So for example, if you're moving a binder over a binder interface, right? So it's kind of like a file descriptor that represents a binder interface, and you want to move it to some other process so they can access it. You want to move that over a binder interface, then you have to use a special call, read strong binder, to pull it off. And if you don't read it with the read strong binder call, you might end up accidentally being passed a binder that the caller doesn't actually have, right? They could just make a reference to some handle you have. But the kernel enforces this for us as long as we use the built-in primitives. There's other things that this does for you. It's not just that validation, but it also will tell you who the caller is, so you can check the UID of the person giving you a message, transacting across your interface. It'll also take care of threading stuff. So you make a call into an interface, that call calls back into you. Well, binder takes care of creating a thread in that other process, having that thread call into that system. And if it calls back recursively into you, it'll take the thread that you called it on and use that to call back so that you don't end up spawning all these threads. It's really important to keep resource utilization minimized on Android because it's mobile phones, they're tiny. Another one is the anonymous shared memory. Oh, one last thing about binder. It's kind of similar to Unix domain sockets in a sense, right? You can use socket options to figure out who you're talking to on a Unix domain socket. They're able to move file descriptors through them, which is great for moving memory maps, very important for high-speed communication. But it doesn't have all these other semantics, so that's why we have binder. Anonymous shared memory. Anonymous shared memory is shared memory that can just be reclaimed by the operating system. And when you create one of these memory file objects, which is the Java wrapper for this kernel feature, you specify a name. And people are used to having shared memory that's named and that they can access. And this is not named, it's anonymous. That's what the A is for. Those names are just little hints. So if you look under like proc pid maps, you'll see the labels that are put on there for the region of memory. So you can tell, while you're debugging the system, what anonymous map is at that address. But it's not some mechanism for synchronizing. New Android toys. So some random images here of purported Android devices. Many blogs like these two have fun speculative pictures. There's a Google source that's been widely cited saying that we're going to have 18 new devices by the end of 2009, which would be awesome. And the thing that I thought was really interesting about that was they said 8 or 9 manufacturers. And 8 or 9 manufacturers, that's a lot of manufacturers making devices that carriers have to take and adapt to their platform and then release. And every time a manufacturer makes a device, they put a bunch of software on there, and they make a bunch of security decisions. And then a carrier gets it, and they put a bunch of software on there, and they make a bunch of security decisions and tweak it up, and then they ship it out. And so, we're going to have a lot of stuff to look at and figure out, what new features are available, and what maybe problems there are. Also, manufacturers don't need Google's permission to create an Android device. Android is released under the Apache license. It's easy for anyone just to take and modify. So who knows how many there really are. So some of the software that comes with the G1 isn't included in the open source version of Android, and isn't from Google either. A lot of features can be spotted just from looking at what's available. Every byte of software that executes on a typical Android device is visible to unprivileged applications, allowing you to have a pretty good idea of what your phone's doing, at least outside of the baseband. So when you get a phone, you should be able to figure out what software is installed on it, anything that's new or cool or dangerous, or features that you might want to use that are specific to one manufacturer or carrier. You should be able to figure out how updates are going to work. You might want to know, do they have something on here for deleting my copy of 1984 in the middle of the night, like some people like to do. You might want to take a look and see what the bootloader's doing, if it's friendly, if you're going to have root access on your device, if someone else is going to have root access on your device, and which apps are system and which are just data. Because things that are put on the system partition have a completely different set of options. They can have additional privileges. They get restored when you do an emergency system restore. Data persists between updates typically. So Donut looks to be adding better internationalization support. So people might be twittering in Farsi on Android devices this year. That's like pretty neat idea. So in countries with underdeveloped law, I hear that sometimes governments perform warrantless wiretapping, and you might not be able to tell who's tapping your voice channel because it's on the switch, and anyone can tap on the switch and there's nothing you can do about it from the handset. But if you want to subvert SSL, it's really important to be on the client. And there are many places you could do something like that in Android, just like there are on any platform. And watching for that is going to be a lot easier on a platform that's open like this than it would be on a platform like the BlackBerry, where someone just got caught doing that the other day. Don't make it so that your battery life cuts in half. So anyway, even if Amazon or Ahmadinejad decide that you need an update, you probably shouldn't be surprised by that. So how are we going to tell? Well, we need some exploratory tools, and Android has a bunch of them. Logcat is the most basic developer tool. It tells you a lot more about the system than you might think. You can safely ignore the SDK's kind of dire warning that debug logs are compiled in but stripped at runtime. You see not just errors and warnings in debug, but also informational and verbose level messages too. A huge amount of logging data is created when using your Android device, and you can experiment with services to see what they log when they get confused, popping things. And so for example, if I send a broadcast intent to something and I give it a null action, maybe the first thing it does is it reads that and gets a null pointer exception and starts logging the error, and when it dies, someone else notices something hasn't been handled, and you can get like a nice little conversation going on that you can monitor. And also don't forget, Logcat has this neglected option, -B, which lets you see the radio and events logs too, so it's not just the main log. And the read log permission is really the hero of the Logcat thing. Anyone with read logs can access those logs, and it's given to the shell application by default. So that's why when you go ADB shell logcat or ADB Logcat, you get nice output. You could have an app though if you want to write some program for doing this analysis right on the device that had that read logs permission. There are apps out there that do that. So Android-specific information is also available from system properties, and it tells you a lot about what's going on. So some of the good things in system properties are ro.secure. So ro.secure is your little hint that any competent attempt has been made to secure this device. Don't type sensitive stuff into a device that has ro.secure set to 0, right? Like, that's not a good idea. If you have ro.secure turned off, you're saying, hey, I'm not trying to really stop the isolation, or I'm not trying to enforce the isolation properly. Usually it's going to be on. ro.debuggable is another one that says whether or not applications on this phone are available for debugging. So if that's turned on and you lose your phone with debug support turned on, someone can just plug into it and maybe debug the system server and get rid of that annoying key guard. That's not so hot. You might want to also look at the GSM version, a real implementation, the RO build description, stuff like that. Linux is a great place to get information. Of course, the procfs is stuffed with useful data, but the sysfs is also a really great place to look because we get the whole global device tree on the sysfs. And when you get a new piece of hardware, you want to know what buses are on here. This is a new chip. Maybe it's got some cool new hardware, some different lights, some interface, a bus I didn't even know about. You can just walk that global device tree and take a look and investigate all that. For example, on a G1, if you look in sys class LEDs, LCD backlight brightness, that file will tell you a number, and if that's 0, the LCD's off. Dmessage, that's a pretty common Linux mechanism. Get into that kernel ring buffer, see what's going on in the hardware, at the hardware level. There's the syscall interface, of course, which gives you everything that you'd expect on a normal Linux system, although it's a lot of it's just available through proc anyway, so you don't necessarily find yourself having to write too much using that. And then, also the file system. There's all these other writable files that are really interesting. I'll go through some of them in a little bit. But sometimes groups also can read information that we might be interested in, and we can join those groups by giving ourselves the right permissions. So APKs that are listed in system app is a good spot to start. That's everything, all the software packages that were on that device when it was flashed by the manufacturer. So. Packages.xml, it's a globally visible file, and typically everything that executes on your Android device is readable by your owner and any application, although the path to that data isn't always obvious. So some directories, like notably data app, they don't have the read permission. So you get this new phone, you want to look through it, and you go into your data app, and you can't see anything. Well, if you pop down into data system packages, you get the path for all those files that are under data app. And of course, all the files themselves are readable. So you can just ADB pull all those files down, take a look at what's going on there. It also gives you lots of details that you wouldn't find in, say, an apt cache, but it's something like that in that it indexes all the installed code, and it gives you this extra information like which ones are assigned with the same thing. Binder information, so there's the procfs has been extended with /binder, so binder's this new kernel thing, and procbinder includes a bunch of details, so things like a transaction log and errors and summary statistics, lists of failed transactions, and in procbinder proc, you find a list of PIDs, those are files. When you look inside those files, you'll find the details of every binder in use by all the processes on the system. So you can actually see how all the processes are using binder to coordinate their activities, what the IPC behavior is on the system. Reading that, actually understanding the logs can be a bit of a pain, but if you look in binder.c, it explains it for you. There's also the dev socket. So Zygot is this really important process on Android. Zygot is the parent of almost all the JVMs on an Android machine. And when I say JVMs, I really mean Dalvik virtual machines, sorry. All the Dalvik virtual machines on an Android machine. The activity manager gets Zygot to fork VMs for it, and then run Java code as the appropriate user for the package that's being executed. This can happen when an activity or broadcast receiver needs to be activated, and so the process needs to be started. Zygot saves the system a lot of memory by allowing Android to reuse the same copy-on-write memory pages for the bulk of the system's libraries. So dev socket contains the Unix domain sockets that are used for talking to Zygot and the radio and dbus and install D and Bluetooth support and all this other stuff, including the property service. This is a great place to go and look to see if new daemons are listening on the server. If they're following the same model as the main code that I just talked about, they'll have a dev socket Unix domain socket for you to connect up to them. Zygot and property service use these and actually open them so that anyone can write and read from them. And that allows you to call into it. And you'd think then, oh, that's dangerous, right? You could just tell it to do something bad. But it uses the Unix domain sockets socket option SO peer cred to figure out who's calling it. And using that, it can figure out your UID and what your rights are and keep you doing only things you should be able to do. And you'd expect that any other services that were built and put on these devices would probably do something similar. Another interesting tool is this dump permission. So every binder interface should probably implement both ping and dump. Ping lets you know the binder is still alive, and dump puts the object's state into a string form and writes it into a provided file descriptor. The dump mostly services, to dump most services, you just need the dump permission, and it's kind of a weird permission if you think about it, because it lets you see everything from the Z order of windows to registered content providers. It doesn't have like a lot of meaning to a normal user, so it's sort of a system permission, but it is accessible to us. And here's an example extracted from the activity provider dump on a G1. The G1 is a Google Experience device, and the Android server check-in package relates to the update system. So you can see from the dump that the clients of the check-in provider include COM Android Vending, which is the Google Market, COM Google Process GApps, some Google Apps stuff, COM Android Phone, the phone, COM Android Calendar, which is the calendar, which why does it need to talk to the update system? And Android Process Acore, which is the launcher, so the main home screen you see. That's interesting information. Android doesn't actually include an update system, an over-the-air update system in the public source. That's something that everyone gets to have the exciting pleasure of implementing themselves. And so for Google Experience phones, I guess they've provided something here. And we can kind of peek into it and get some idea what they're doing. Obviously, this is a great thing to study in order to figure out who's talking to who. The main drawback of using dump is that there's no standard for how to format the information. It's all just how the developer decided to do it, so it's not easy to make it machine readable. You end up typing in a lot of regexes if you want to parse it out and make a graph or something. Android systems have, the Android system has a single Android manifest.xml for the whole platform. It defines the system's permissions and some of its features. Every application also has its own Android manifest.xml, and every APK's Android manifest defines some of the key security policies for its code. So for example, which parts of it are exported attack surface? Right? We know that when we export a content provider or an activity, it can be called, it's going to run as us, not as the caller. So that's that's basically an attack surface, right? There's a privilege barrier, there's communication happening across it. If the person communicating to us says something mean and we fall for it, that'd be bad. So they define all these attack surfaces. They also define permissions, what PIDs things run as, all kinds of other interesting little bits. So the XML files are really important. Unfortunately, they're also a bit tricky to view, as in the APKs they've been compressed and they lose a little of their data in the squishing. My Manifest Explorer tool that I'm releasing today helps you investigate this critical information source. Also, there's system services. So these are there for a reason, right? They basically offer this huge interface to the system. And one of them is the package manager that I use in my tools. It's the package service. The activity manager has the activity service. And some of the things I use are non-services like settings. You can start up their activities and ask them to do some stuff for you. And when settings starts things, it starts them as a system, and it can do stuff that you might not be able to, like it can delete the data for an app, which is nice. So how do we apply these exploratory tools? One interesting thing I ran into while reading the Cupcake code was secret codes. So secret codes actually sort of come from Android. From the private parts, which app people aren't supposed to concern themselves with. So the telephony class contains an intents class, which has a few constants, and one of those is shown here. The comment makes me think the dialer supports this thing called a secret code, which I think is very cool. So we fire up grep and we tap in secret code and we see what pops out. And nothing pops out in the framework other than this, of course. But under packages, in the contacts, we see the special car sequence manager. So contacts, that's the little program that handles dialing, right? I mean, that's a good place to be finding a special character sequence manager that relates to secret code. And voice dialer receiver. Must use them. So let's take a look at them. That special character sequence manager has a little code in it to handle these secret codes. It nicely explains in its comments what's going on, both in the code and the comments. When you enter the code *# code #* into the dialer, it broadcasts an intent. The intent has the action secret code action. We saw that defined earlier. But its target is resolved by activity manager based on the URI of its data. This URI always has the same scheme, which is Android secret code, but the host portion of its URI is the value of that secret code. There isn't anything else to the intent, so the receiver has to know what it means and react to it. If you enter an invalid code, the intent will still be sent, but the activity manager won't know who to broadcast or who to route that broadcast to, and it'll just drop. That'll be kind of boring. So one party that was the other hit for our secret code action grep was the voice dialer receiver, but when we look at it, we see that it just uses it to turn on and off some debug log stuff. It stores the debug logs privately in a place that no one else can read. That's kind of boring. But let's take a peek at it anyway, just to see how it gets these, right? Because we might want to see how other people arrange to get these so that we know when other people want to hear secret codes. So if we take a look here, the voice dialer is this program that doesn't actually have a lot of privileges. It actually can do one thing that's very sensitive, which is make calls. We see here that the secret code action is used on a broadcast receiver's intent filter, and the data scheme is what we expect. But in the host, we have two numbers, 8351 and 8350, or as the comments read, VDL1, VDL0, so voice dialer log on and voice dialer log off. So now we've seen that. Let's take a look at something else. So Manifest Explorer. The idea of this tool is to see what the installed Android manifest.xml files say. Accessing the system's Android manifest is probably the most important one if you're looking at a new Android device and trying to decide what's new. Indeed, the first version that I wrote of this program was for the pre-open source versions of Android, when I wanted to see the system's Android manifest just so I can understand what the permissions were, what the security model was in this platform. I believe I mentioned earlier how you can read every byte of executable code on your device without any special privileges. Well, Android manifest is installed on the system, and it's also accessible from every process. So you can always dig around and find them. The only little drawback is that they've been compressed because they're designed to convey information to the system. They don't need to be pretty, and this tool makes them a little easier for us to use and view, and kind of uncompresses them. So here's what Manifest Explorer looks like. So on the left, you can see the sort of starting view. At the very top, you have a package list. You pull that list down, and you get the view in the middle there. Scroll through. This is everything that's installed in the system, every package. And packages are kind of like applications. And these names are the true names of the application. True name of an application is really important. You can actually have security problems if you call out to something and there's a race where someone else installs that package first. No two packages can have the same name. It's very important that you get your package in early, which is why a lot of packages get installed with the system instead of being downloaded after the fact. I've got a view here of, or once you've selected a package, you can tap the view button. It'll update the text view with the content. And if you hit the menu button, you can get this save option and save this out. So you can read it in 1920 by 1200 instead of in tiny little telephone squinting. So here's how a Android manifest should look, as opposed to how it does look in Manifest Explorer. This is the browser's manifest. I just pulled it right out of the SDK. And it starts off with a very nice comment. And look at how nicely indented everything is. And that's good. And this is what it looks like when you're looking at it in Manifest Explorer. It's not as pretty. The comments are gone. They're removed during compression. But all the useful data remains. So now let's use this to dig around an actual Android device that isn't open source, the T-Mobile G1. So here we have an application that came on the device. Indeed, it appears to be privileged code. As you can see in the leftmost image, the top of the manifest, it has a shared user ID of android.uid.shared. So this is a program which must be proprietary to T-Mobile and doesn't appear online in source form that I'm aware, and I certainly don't have its original manifest. Yet we can extract the manifest well enough. As you can see on the right, near the bottom of the manifest is the broadcast receiver that they've exported. When you export something, that means you're allowing other people to call into it outside of the package. So this receiver is filtered with the secret code action and requires data with a scheme of Android secret code. And this should sound pretty familiar. The host that they've configured is 87695. So this is their secret code. Okay, it's probably not a nuclear launch code, but it illustrates how we can look into what people put into our otherwise open platform, the little proprietary bits that get stuck in there, and we can dig out what they're doing and maybe play with it. Also, if something is actually secret, I don't recommend storing it in a file marked O+R or distributing it on a device that you sell or even checking it into a source repository. The idea of secrets is an idea for user data, not for code. Software isn't secret. All right, so what's the secret code actually do? So I don't really know. I noticed I received a WAP push SMS after the system prompted me for a number, which I just left as their default, 453. For looking at this in more depth, we'd probably want to decompile it. There's a guy named Mark Schoenfeld, I hope I didn't just butcher his name, from the University of Bamberg. He's built a tool called undx, which is illegalaccess.org/undx. I read his slides, and they're very impressive. His tool could probably help us take this apart and reverse it into some Java source code, but I'm not going to do that right now. I'm just going to show you what the WAP push that I received looked like. So there's the hex of its PDU. If you've been watching any of the other mobile talks, there's been a lot of talk about hex PDUs. And also the logcat log. So this is a selected 6 seconds around the time I tapped the code in, and you can see, some details of the message, which parts of the software are handling it, what they're doing, sending and receiving. It gives you somewhere to start at least. So that's it for Manifest Explorer. Now I'm going to jump into another tool. This one's called Package Play, and it shows you the packages that are installed on your system and lets you explore what they allow software to call on them. So you can see, for example, all the activities, whether or not those activities are exported, all the services, whether or not the services are exported, broadcast receivers, content providers, instrumentations, and the permissions that they have the system enforce upon their being called. It also can switch into Manifest Explorer or into the settings application to view the content. And here's what it looks like. The first step with Package Play is to select the package that you want to examine. So there's this all package at the top, which is just a synthetic package which shows you everything for the whole system. It takes a long time. Usually you want to select some particular piece. So in this case, I don't remember installing something from HTC. They're the company that makes the G1. And now that I think about it, this is a field test is something that a hardware company might want to include for fun on their phones. I don't see this application showing up on my home screen or application menu, even though it's installed on my phone. That's because this activity doesn't have the category launcher in its intent filter. And such pieces of application functionality are really common, but they're not always easy for us to see. So we can start this one up using Package Play just by hitting the Start Activity button. And we can see what it does. This will bind the intent to it explicitly and launch it just like any other activity. This doesn't always work. Sometimes things just crash or nothing happens. But this one works nicely. There's lots of little hidden pieces of stuff floating around on your phone. And this is just one example. And one of the features of Package Play, obviously, is to list and start all the exported activities. So this is what it looks like when we start up the field test. The activity starts, and we get the option to hit the menu button. And when we hit the menu button, we see all these test items. And that sounds like a lot of fun. There's just tons of them. They all relate to phone stuff, GSM, WCDMA, 3G uplink transport, stuff that I don't understand. And then we actually select some of these, and here's a couple of views. You can see all kinds of neat little signal information here. So lots of data gets displayed, and the log cat starts chirping away about radio interface layer requests. So you have to be a pretty special guy to send a radio interface layer request. And we didn't see this thing requesting any permissions when we looked at it in package play, right? It said it didn't use any permissions. So you better check out the field test's Android manifest and see how it gets the ability to be such tight chums with our radio. So we hit the back key, leave our activity that we just started, and we go into the manifest by tapping the See Manifest button. And, right away we can see at the top that, I don't know if you can read it, but it says shared user ID equals android.uid.phone. So the phone, it's going to share a user ID with the phone. That's pretty tight. And just underneath that you can see process com.android.phone. So it's not just going to share a user ID with the phone, but it's going to actually ask Activity Manager to start it inside of the phone's process. So this is this activity is being started inside there. It runs as it. So if you look at it with PS, like I've got a little line from PS down there that says radio 100. So that's PID 100, and that's what my field test was running as. And the reason it has such a low PID is because it was started when the system was young. All right, Intent Sniffer. So Intent Sniffer is a tool that is designed for watching runtime broadcast intents. So you might send broadcasts to notify people of events, or there's lots of broadcasts going on all the time. We'll see some when we look at the UI. It doesn't see explicitly broadcast intents. They're not broadcast if they're sent explicitly. They're just sent to the exact person who received them. Activity Manager doesn't dispatch them. And it defaults to seeing mostly unprivileged broadcasts. You can put privileges on broadcasts. You must put privileges on broadcasts of sensitive information. This defaults to mostly unprivileged ones. If you want to see privileged ones, just recompile it, add the use permissions, you're good to go. And you should definitely be doing that if you have permissions that you think are likely to be used in applications and that you're using to protect things, and you want to be careful you don't leak information that you shouldn't. So it also has an option to see recent tasks intents. So when you start an activity, you give it an intent. And that intent actually is visible to other processes. I can say, hey, show me the recent task list, and I can look in there and see the base activity that was used to start that intent. And if it's got a bunch of extras in there, that's a bit of information leakage. And the application can also dynamically update how it receives information. So one of the things it can do, or one of the things it does, is when you install it, if you update the packages, it'll reflect across the actual version of Android that's installed on the phone, and it will use the actions that it finds to find both kind of inside some of the system services and some of the private parts of Android, as well as on the intents package. So say someone decides to change the over-the-air update intents so that they're slightly different, you'd be able to notice that, and it'll listen for the correct one. Oh yes, types. So whenever you're intercepting intents, you need to hit the types and the schemes as well. Types are wildcarded, so you can wildcard types. Categories are looked up dynamically based on what's actually installed on the phone, and schemes are hard-coded. But I think I've got a pretty good list for what's in Cupcake, at least. So here's an example intent that's found by the Intent Sniffer. Of course, so what I've got here is an intent that looks like it's a task that's running, and it was started by this intent, and its component is com Google Android System Updater, and it's the System Update Install dialog. And this is the little installer dialog that might pop up and bug you about installing an update. And if we look in it, we can see the update file is in cache, signed, killa, OTA, blah, blah, blah. So of course, we can always download this file from the update server and have a look at it, assuming we downloaded the same one that the phone did. That should be true unless someone is really interested in you, in which case you have problems that I can't help you with. I hope you're in a free country. Normally, when I see something like this, I would think that it's from the network operator or manufacturer, but this package name sounds like Google, and I doubt that Google's partners would be using the company's package names without their permission, so this is probably something that's part of the Google experience, and it isn't in the open code. So here's what intent sniffer looks like just with its menu up while not sniffing for any intents. A couple of buttons. The show stats button tells you what's been found in terms of dynamic action and categories discovered for broadcast intent sniffing. The update action button can take a while, but it does that reflection across installed classes that I was telling you about, as well as walking through the Android manifest for every installed package on the system, including the system packages, looking for any broadcast receivers, finding their actions that they're filtering it with, and adding those to the list of actions for it to sniff on so that it sees everyone. And you can see from this little list here that I found 114 of them through reflection and 25 of them by manifest registrations. And it doesn't count things twice. So anything it finds, it does the reflection first. It found 25 more by looking at manifest registrations. So here's what it looks like in action. You check the boxes for the kinds of things you're interested in. If you check show details, you get a little extra information. It shows you the extras as well. You have to tap the refresh button because when I made it automatically update that, it wasn't possible to watch. And the intent source is listed at the bottom of each intent. So intents with components are obviously tasks, and because we can't get explicit intents normally. All right. And one of the other things I thought I'd point out is that if you're starting an activity and passing in data in an intent, like we just saw was done by the updater, that intent shouldn't have anything sensitive in it because it's going to leak out potentially to people that have the get permission privilege, so like my intent sniffer just did when that information leaked out. So this is kind of like that old problem you might have when you put a password on the command line and it shows up in everyone's PS and you feel like a fool. So avoid that. Intent fuzzing. This is ill intent, a silly little intent fuzzer I wrote. Fuzzing can be a lot of fun, but actually Java minimizes the fun. It turns out that it often finds crashing bugs or performance issues. Not usually, the buffers aren't going to be overflowed on stuff that's written in Java. Even though you're not in the Java security manager, you're not in the Java sandbox, you are taking advantage of the language's type safety to get the security benefits of Java that are kind of due to the mechanics of the language rather than the advantages that are due to the underlying class library or the class library's integration with the security manager, which, by the way, almost nobody uses outside of applets. So you can fuzz either single components or all components, and this works well on broadcast receivers and okay for services. Services are started, but they never get stopped. It also leads the out-of-memory killer to get real busy, because as you're launching all these processes, the out-of-memory killer is busy murdering them. What it does in terms of fuzzing right now is it just sends nulls, null actions, null categories, null extras. One of the most common problems you find in Java code is mishandling of nulls, because it has a pretty good time with long strings and stuff. But null pointer exceptions will pop up. This can put interesting data into the log, but most good fuzzers are domain specific, and when you have type-safe languages, that's especially true, as the most interesting flaws are in the domain of that program that's being tested, not the mechanics of how it's implemented. So I often fuzz things with the am command too, like intent fuzzer. You may want to rebuild this program with additional rights if you're attempting to fuzz something sensitive, like a product you're building. I hope that at some point to be able to update it with some additional fuzzing for bundles past instrumentations and other nasty data to use as kind of samples. By the way, fuzzing services will give you junk on the screen on some versions of Android, and it's not a malfunction. These are development services that are there to help users understand CPU and processes that are running in CPU use. That can be kind of fun to look at, but it's not the end of the world. And this thing will also cause the system to crash. And crashing isn't fun, but it isn't actually a huge security risk on Android like it is on normal systems. The system is like Android applications are actually designed to be killed and restarted by the out-of-memory manager. That's part of the life cycle of an app, is being murdered in its sleep. And it's not like on the out-of-memory killer will do that on your normal Linux box too, but on an Android phone, it's expecting it. And it happens a lot, whereas your OOM killer might not even be used on a normal server with 4 gigs of RAM. So you should still try to make your applications robust against this kind of stuff, but you're not going to get very far calling it Leet 0 day. All right, Android's private parts. So Android Intent Sniffer had some hidden pieces of the platform that I needed to use. I needed to find actions that might be interesting for us to sniff for, but they're maybe deep in the telephony stuff. They're the kinds of things that aren't in the SDK. So code that directly accesses hidden parts of the system won't compile in the SDK by default. So to make my code easy for other people to use without having to set up a Linux machine and build a special APK for yourself, a special SDK for yourself maybe, I just dynamically load the classes and use reflection to find the pieces that I need. That kind of brings up Java's security stuff, or method level access control, like private and protected and public. And those don't mean anything in Android, right? They're there to help the programmer avoid accidentally making their code, whatever. From a security perspective, there's no boundary at all. You can just change it. There's no security monitor. You can just go into the reflection APIs and say, yeah, that field, it's accessible now, and it is. So, so it's key. I hit this problem so often. People don't necessarily quite get that that even if you were to change the class library so they wouldn't do that, that still wouldn't make that impossible, right? You could just run code that did that, native code, right? You could write your own VM and launch that. You have real total native code execution on Android. The sandbox is at the Linux level. So there's about 1,000 hidden classes and methods in Cupcake. The code is sometimes more hackish than that nicely polished SDK. And there isn't a conspiracy going on that I know about, but this is really there to make it so that developers don't accidentally link against the shakiest bits of the platform. As the platform evolves, recently they've added support for input devices, input mechanisms. In Donut, they're adding a bunch of internationalization support. You don't want to end up using something that they know they're going to have to change. So obviously, when we're security researchers, we need to bypass that, and it doesn't make any attempt to stop us from doing that. So you might just have to change your path around a little bit in order to compile the stuff that you want to compile, or use some reflection if you want to keep the code easy for other people to use. So root lockdown. Carriers and manufacturers that don't allow users to have full rights on their own devices risk those devices being controlled by others. So users who want root may be a small group, but they may avoid updates in order to wait for some kind of exploitable privilege escalation bug to be fixed that they can then reverse and use to get root access on their own system. So ghetto schemes for keeping root are actually really easy to exploit. So one thing that you see all the time is people leaving setuid root shells floating around on their system partition, right? Like, having setuid shells is a bad idea, because sure, you can use them to get root, and so can your block stacking game and anyone else. It's not a proper secure mechanism for keeping control of your device. So this combination of unpatched systems with intentionally vulnerable configurations and is kind of the opposite of secure. Right? It'll be the network that suffers if worms or malware take advantage of that misconfiguration, and the network that decided to force people to get into this circumstance will be the one, I guess, that'll get to pay for the cleanup, which I guess is kind of fair. So if we contrast that to programs that grant users root and then secure it competently using passwords or user interactions to validate users' intentions, those programs will give the minority of users who need root the ability to develop and experiment on their devices and keep them happy and willing to update with all the latest updates so that they aren't vulnerable to some buffer overflow in the codecs or something like that. I mean, you don't want this sandbox is really important. We know from having software for the last however long we've had software, that it has bugs. You have to patch the bugs. If you're not planning to patch your system, you're not planning for a secure system. So even, you don't undermine that. Also, is it really likely that that a Linux-based operating system is going to have no localhost privilege escalations for some kind of commercially meaningful period of time? Like, that's not, if you look over the last couple of years, it hasn't done that well. So, you're probably not going to actually be able to lock out people who are naughty. All right, proprietary bits. So I know that we're all familiar with software that we don't control. On the x64 versions of modern Windows, you can't even patch the kernel to spy on device drivers that want to implement DRM. This is especially true in hardware land, and the FCC has some reasons for this. Not every FCC regulation is a bad one, even if these ones are. And it's hard to monitor SSL connections from the switch, but it's actually not that much easier to do it from radio firmware. I'm not saying it's impossible, I'm just saying it's difficult and it's very configuration dependent. You have to know a lot about what's going on in the application level to monitor an SSL connection from the radio baseband. And that also depends, of course, on the device's configuration. It's a lot easier to do it in the application level. Android makes this boundary actually very clear, and hardware platforms kind of muddle it up again, right? So you've got this very simple, nice model, and then you've got this system on a chip, and you don't know who made it, or you do know who made it, and they say, oh, the documentation for it's completely secret, and we won't let you see it. And maybe they've got some crazy part of their software that can touch physical memory, or something's a bus master, and you don't know. That's a bit tricky, and it's something that you've been dealing with for a long time. Your computer has a BIOS, you have a Wi-Fi card, and your Wi-Fi card has some firmware that you're loading into it, and you don't know what that is. You can spend a lot of time worrying about this kind of stuff, and there have been some presentations about how this stuff can be something that's worth worrying about. You don't want people reflashing the firmware on your network cards to run its own little system. But do you really know what's at the heart of your CPU? Do you even know what vPro is? I just see the ads for vPro. I don't know what it is, but it says that it lets people manage my Intel computers when they're off. That doesn't sound like something I really want. But anyway, so there's all these little things that are really deep down inside our systems that we don't understand, and the way to handle that is to put clear boundaries between them and then try and figure it out. So we need to keep ourselves away from GPL purity combat, or we'll never get to have the powerful toys that we want to have and build the systems we want to build. But we have to kind of keep perspective and a disassembler. So I highly recommend searching the net for platform documentation. One thing that's great about NDAs is that people break them by accident, and then people on blogs jump on that. And anyway, there's some great documentation out there about some of these radio chipsets. Let's see. Oh yeah, and if you're a carrier that wants to spy on users, you might want to avoid offering Android devices, because there's a lot of other platforms out there that hide everything related to the updates and to system configuration and to software from users, right? This is, Android is minimizing this huge kind of natural complexity that's in mobile phones. It's not good for that. So common problems. When you're looking at Android applications or code, you're going to see a lot of different kinds of bugs. I just wanted to kind of briefly talk about some of these. One of them is implicit versus explicit intents. So when you start a service, say, or start an activity or send a broadcast or whatever, you're sending an intent, and this Android runtime is going to bind that for you. If you know who you're sending it to, make it explicit. The only kind of catch for that is if you're a system service, so if you're a carrier service, you don't want to necessarily mark things that are explicit if they're not also system services, because when you start the system in safe mode, that code might get run. One of the big mistakes people make is having too many or too few permissions. If you build an application, the permission set has to be reasonable and minimal. It has to be something that a user can understand. So if I have a shopping list, it's okay to have a access shopping list permission. It's not okay to have 15 different kinds of permissions that no user can understand, right? They'll just have to grant them all. And it's no good to have just one permission for a whole platform if you're building a platform, because they can't have separation of privileges. Data sources and destinations. So when you look at code a lot of the time, you see people who are receiving information and they need to make sure that they know who the sender is, and people who are sending information and they need to make sure that they know who the receiver is. Usually you use permissions for this. Occasionally you might want to use package names or explicit intents in order to do that. But permissions are really the right way to do that. And I'd say that half the time, or some meaningful percentage of the time when you're looking for bugs in this, someone's secured it half the way and not the other half. And they just kind of got halfway there. They're like, oh, we applied a permission, and they only applied the permission to make sure that the user, or the app calling it, had the permission. But they didn't apply it the other way around and make sure that someone couldn't see it, that shouldn't be able to see it. So trusting external storage. So FAT32 gives you no security for you if you're on FAT32. Don't write files there that you think are sensitive. Don't log all your SMSs there. Don't put data that's protected by Android permissions there. If you've got data that you're not going to protect, like say the pictures from your camera. Pictures from cameras are really big. Movies from cameras are really big. They're not good to write in an AND. So what you do is you put them on the flash, right? And they're insecure when they go on the flash, and every app can see them, and you don't give the user a false sense of security by saying, see pictures permission, right? Because that's total BS. If you want to go through the trouble of building a content provider that uses that backend store and encrypts the data as it goes in, and then stores a cryptographic key, which is nice and small on the NAND where it's safe, and then using a camera that stores its pictures that way, now you can go to the now you can say, oh, see pictures, right? Because you've actually got something to protect. But anyway, users with unpassworded setuid root shells, SU, etc. Talked about that. Implementing non-standard features. So there are features that you must have and that are not included in Android. So for example, everyone wants to have over-the-air updates. Everyone wants to have the ability to distribute applications. Everyone wants the ability to update those applications once they've been distributed. Those are features that people build into devices, but if you're not putting together a Google Experience device, you're going to have to build that yourself. And even if you are, I'm sure you have some amount of customization that you're going to probably need to do. So that's a pretty tricky thing to get right. You might want to spend a little time thinking about that. So I'd just like to thank some of my coworkers, especially Chris Palmer, for giving me feedback, and Jonathan Wilkins, and as well as the Google Android team, who are totally awesome, and a bunch of my clients who can't be named, but who help keep my mental hamster in shape. Any questions? Yeah.
You mentioned when you were talking about fuzzing that intents are handled by Java code, or Next, and so would be resistant to fuzzing, but aren't any intents handled by unmanaged dynamic fuzz interfaces?
They could be handled. So the question was, can you have a broadcast receiver that's written in native code, and wouldn't fuzzing that be interesting? And you can definitely have one that's written in native code. It's not done very much, and I haven't tried. I mean, I've tried a little. Any others? Or maybe my suggested questions will help someone ask a question. Yeah.
Working so much with Android, do you see that there's going to be an upshot in actual adoption of mobile? Or there's a lot of talk about this being like the core of like other things for OSs and like on bigger devices?
Yeah, I think mobile is where it's focused at. I think the announcement of the Chrome OS says that that Google might even be focused on keeping this mobile. I mean, it's hard with netbooks and mobile devices. Kind of the lines are blurring a little bit. My laptop has a CDMA, or has a radio card now. It has a GSM modem. It has all the same kind of interesting stuff that a phone does in a sense. It's.
Do you see it being an uptick now, like market share?
Oh, I don't know. I don't follow the business stuff enough probably to give you a good answer on that. But yeah, I definitely think it's probably going to really spur mobile adoption, especially the fact that the cost of these devices is going to be much lower because there's no licensing for the operating system level, no VM licensing. That's a big savings. And on devices that are heavily subsidized by carriers, like a cost savings like that can make a real financial motivation for deploying something. Any other questions? Yeah.
What is the deal with code signing that doesn't require a trusted root? I mean, shouldn't I have to eventually trust a monolithic bureaucracy after we're verified?
Yeah. So it turns out that who has a credit card isn't necessarily the best judge of a person's character, and that actually good guys can, or good and bad guys can have credit cards. So code signing isn't. Code signing, it has advantages, right? And I don't know that that model isn't going to be the one that wins eventually, even on Android. There's absolutely nothing stopping a vendor from building a version of Android that uses code signing, right? It'd be very easy to modify the package manager to require a VeriSign certificate or an Apple certificate or a T-Mobile certificate, right? It wouldn't be hard at all to hard code that kind of thing in. And in Europe, some people try and do that sort of thing on Windows Mobile. And there's people that do that sort of thing on other platforms, not on Android. The big advantage of not requiring someone to have a credit card is that you get a lot of people that are willing to play and willing to play for free, right? And a lot of the apps on the Apple Store cost money, and a lot of the ones on Android are free. And that's a big advantage. And if you kind of punish people by requiring them to have a cert, then maybe they won't give you the toys for free. It's then what it also works on, though, is the reputation, right? If I write a good application, I get a reputation, and now you're willing to install my other application. And if an application starts getting a bad reputation because it's causing the system to slow down, it's bad. I downloaded one the other day, and it had a really nasty EULA, and I didn't even bother playing with it. I just said, low ratings, deleted it. That's a pretty reasonable protection. Unfortunately, that whole marketplace experience isn't actually part of the cupcake, like the open Android code. That's something that's outside of that. Yeah?
What's the deal with code signing that doesn't require a trusted root?
That's what you just asked. But yeah. Code signing that doesn't so trust roots, not necessarily. Yeah, it verifies that it's you. So if you write an app and you write the update to your app, you better use the same signature for it, or it won't be able to install. Remember I mentioned earlier that the true name of an application was its package name? You can't install over top of my package name unless you have my signature. And so that doesn't have anything to do with the trust root. So that kind of security can still be attained, and that's actually a pretty important security benefit. Also, I can tell maybe what other apps you've written, and so I know, hey, you already wrote my email app, and it's worked really well, and it's trustworthy. I'm going to install his Tetris game. No problem. Right. I think I'm done. So there's some places to get the tools and a contact address if you want to email me about anything. Thanks very much for listening.